So we got page 8 started last time. So let's go on and finish this one. We had someone pulling on an object, yes, with a string. And so we used tension force, but I don't know if I said it last time, but they do say the words applied. You could have also called FT, FA, as long as you don't do both, okay? And so I didn't put that on here, but we could have called either one, FA or FT, okay? And so we're pulling at an angle. And so you have to recognize that the angled forces, it's a vector, they have components. And so finding the components here in a second, got to do some trig. So hopefully someone at your table has a calculator. Go on and do a quick check, make sure it's in degree mode, it matters. In this one, they said there is a constant speed, which we already addressed, means zero acceleration. And in terms of forces, that means your net force is equal to zero. Newton's second law, F net equals ma, but since they're equal, since they've summed to zero, that means you have balance. So it's also Newton's first law. Good with the recap on this one? All right, so what do they have us solve for? Sum the forces in the x, check. We defined our positive direction as forward to the left. And so FT, but the most important part there is, it's just the x component of the tension or applied, okay? That's the left horizontal force minus the frictional force. And that's actually what we're going to be solving for with part A. And so next step, let's isolate friction. And so we're going to add frictional force to the other side. And then we'll have to subtract F net to the other side. And so we would get frictional force equals FTX minus F net x. And again, using the subscripts, you cannot mix and match. You cannot mix the x and y forces. They're independent dimensions, just like they were in projectiles. And so, now before we find FTX, F net in the horizontal when traveling constant speed velocity is going to equate to what? We've already said it once. F net will equal 0. And so you can go on and zero it out, or what you may see other problems do, and it's not a bad thing, okay? At some point you have to recognize it zeroes out, but maybe you're like, oh, Newton's second law, F net equals ma, and then constant speed, there is no acceleration. And so F net does zero out, which means the frictional force, that's okay, phone and laptop. We're picking up on page 8 where we left off. It's recording. Oh. It's recording.
No, just search it. It's not like anything like personal.
Okay, hold on. Okay, so F net zeroes out. Force of friction is going to equal not tension, not 200, but the x component. So we have not found the x component yet. And maybe you see the triangle there. Maybe we kind of zoom in on that. Hold on. Okay. Maybe we zoom in on that tension force. I like to draw it bigger. So it has an x component and a y component, and there's our angle. And so what do we know about this tension? They said it's 200 newtons. That's the actual force. That's the diagonal force. And they told us 30 degrees. So looking at our vector, how do you find the horizontal component? Which trig function? Cosine. And so we'll use cosine for the x. Now, here in a second, we're going to be doing vertical. What trig function would we use to find the vertical? Sine is tradition, but true story. If you know 2 out of 3 sides, you could do Pythagorean, you could do tan, but just tradition, what you see in the textbooks is going to be the sine component. And so just like we did with projectiles, I'm going to plug in my hypotenuse. I'm going to use variables first. Hypotenuse is the tension force, and then times cosine theta is going to be our equation here. And again, a lot of times angles are with the horizontal, but it's not 100% of the time. So always reevaluate, look at where the angle is adjacent to. And so now we can plug in our numbers, 200 times cosine 30. This is going to be our frictional force. And someone grab a calculator. What is 200 times cosine 30? $173, and the SI unit, our component has the same unit as the hypotenuse, which was newtons. And so there's your frictional force. Now, some of you may be thinking, oh, I thought friction was always backwards. Shouldn't it come out negative? So just moral of the story, the way forces is done, we already made friction negative in our FNet statement, okay? And so AP does this, because it's not always about a number. They do it in the variable system, okay, statement. And so, yes, we've already said friction is negative, so we're really solving for the magnitude. If they ask for magnitude and direction, you just have to remember, oh yeah, it's to the right on this problem. It's back, right? Okay. Now let's do the vertical. Sum the forces in the vertical, and then use our FNet statement, our summation statement, to solve for the normal force. And so kind of, getting an eye for that diagram. How many vertical forces do we have? Give me a count. How many? There's 3. If you see 2, you're forgetting about the component, okay, of tension. And so FNet in the vertical. Now, previously we said that up was positive, just went with standard. It's not moving vertically, and so it's not going to matter. And so I'm going to say Fn plus, keep me going. Who else is going upward? The y component of tension. And then gravity is 180 degrees. It's downward, so plus a negative or minus Fg. And we're going to use this equation that we just wrote to solve for normal. Y'all, moral of the story, most of the problems that are like this, the equation is not on the formula chart, okay? There is no tension equation at all. Now, there is a friction one, but we're not using it till next week, okay? There's not an equation for normal force. It's all going to be through your FNet statements most of the time, okay? How do we write these statements? Got to get your diagram right, okay? So let's isolate Fn. And so Fn, we need to subtract Fty from both sides and add Fg. Now, I'm not changing the direction of gravity. The direction is down negative, but I'm doing the algebra to isolate, solve for normal force. And so we'll end up with Fn equals Fnet y plus Fg. Well, maybe I should have showed a minus. Negative Fty. To me, that looks weird. I like positives first, but I wrote in reverse, whichever. Okay, let's start plugging things in. And so Fty, we already said we'll use the sine function. And so it would be that hypotenuse, Ft, times sine theta, plus, and y'all, question of the year, how do I find the gravitational force of an object? What do I plug in for Fg? Fg equals mg. And I'm making a point about it because a lot of students, they just go too fast and they're like, oh, G, 9.8, done. If that was true, then every object that you had in a problem would all have the same weight. FG is weight. Weight is more than 9.8. Remember we talked about going to the moon? Our weight changes, but we look the same. We feel the same in terms of clothes fitting type. And so it's mass times the acceleration due to gravity. Plus look at units. G, 9.8 meters per second squared. You can't add or subtract that from a Newton. And then F net Y, F net is Newton's second law. F net equals what? What do I plug in for F net? Not a number. What variables equal F net? This one is on the formula chart. MA. They have it A equals, but solve it for F net. Newton's second law, F net equals MA. And so there's your variable solution, and it's a vertical acceleration. And so questions on the variables. All right, let's start doing numbers. So I'm just going to go on the right-hand side there. And so a negative FT is 200 times sine 30 plus mg. So I got to scroll back up. I forgot what mass they had. 50. And we said kilograms is good. And then G, 9.8. I'm going to go on and use 10. And then mass again. What's your vertical acceleration when you pull this box and it moves horizontally? Vertical acceleration is 0. Now, I could have zeroed it out earlier, but I do want your habit to be F net equals MA, F net equals MA, F net equals MA. Is it going to zero out every time? No. And so I don't want you getting zero happy and zeroing it out every time. And so now we got our numbers. This goes away. 50 times 10 is 500. And then 200 times sine 30. Maybe you remember sine 30 is 1/2 or 0.5. So half of 200 is, what's our normal force here? 400. Does it make sense that it's less than your weight? Fn numerically came out less than your weight. Should that be the case when you pull up on an object? Yeah, not that you're lifting it off the ground, but you're not making the ground work as much because there's less pressure with the ground. So there's less force with the ground. Yeah. Okay. It's not levitating though. When I say you're lifting it off the ground, I don't mean it's levitating. Okay. How do we feel on that one? Okay. I'm going to have y'all try number 4. It's the same picture, but watch out. A 70 kilogram box, so we just changed the mass of the box, is pulled by a 400 Newton force, so a new force. Same angle, 30 degrees with the horizontal. Now we give you friction, 75 Newtons, and we're asking you to solve for the acceleration. So similar but different. Can I ask, do they say the special words, it's moving at a constant speed? No, because earlier, acceleration in both dimensions was 0. But here they're having you solve for acceleration, okay? And then B, how far will the box go in 30 seconds? Sounds like what topic to me? Kinematics, okay? And note to self, 30 seconds in physics is actually a long time, okay? Physics is quick. And so you're gonna get a big number, it's okay. You're gonna get a 4-digit number, it's okay. And then determine the normal force, okay? And so I'm gonna give you about 5 minutes. Give this one a try. If you want to check answers, I'll show you at the end the answers, but if you want to check A before you do B, that's fine, okay? Because B actually does depend on A. All right, try the bottom of page 8. So for part A, the diagram looks the same as it did above, right? Your FNet statements are actually the same as they were above, except you're not going to zero out AX, FNet X. And so your FNet X statement would be that forward tension X component minus the frictional force. FNet equals, we got to be quicker on that. FNet equals MA X. Now, previously, we zeroed that out. We're not gonna today. And so to solve for that acceleration, it would be the FT cosine theta. Again, it's very similar to the one above. If you draw your tension triangle, the X component is adjacent to theta. And then minus frictional force, they actually gave us. And so after you do that summation of forces, you'll divide by the mass, okay? And so you should get about 3.8, 3.9, somewhere in that region. Good deal? And then for B, kinematics, how far does it go? It tells you up above. Nope, it doesn't. 30 seconds in the question there. And so we know the time, we know the acceleration. Now you do have to make an assumption. All of our kinematic equations have initial velocity. What's the assumption of the initial velocity? It would be 0, right? And so we'll all assume it starts from rest, okay? The way I look at it, 30 people can't decide on a number that's not 0. And so you'll assume it starts from rest. And you should have used the second equation. And you just plug in the acceleration from above. Time is 30, then you're going to square it, hence the huge number, and you get 1,700 something. Okay. Normal force is a vertical force. No equation on the formula chart, so you need that FNet Y statement. And so again, similar to above, I think it's identical. Fn plus Fty minus Fg. Fnet equals what? Well, before 0, Fnet equals MA. Now, that's a vertical acceleration. Don't plug in the acceleration in the horizontal into vertical acceleration, okay? A lot of students want to plug it into both places, acceleration, acceleration, but it's independent of the horizontal. Vertical is independent. And so as you pull on this object, it only moves in the horizontal. There is no vertical motion right here as I push my cart or pull my cart, right? Some students want to plug in gravity there. They're like, gravity is a vertical acceleration, but careful, we'll take care of gravity with Fg. It's not a net acceleration, okay? And so this does 0 out. And so to solve Fn, move those two to the other side, just like last time, and we get a positive Fg minus the Fty. And I think it turns out not same number, but same variable, right? And so mg and then minus Ft sine theta. It's a different number because we gave you a different tension and a different mass, right? And so I think you should get, with 10, I got 500. Questions on pulling an object, or you could do the same thing with pushing, right? I think the practice quiz in Canvas has a pushing example, okay? We already looked at that diagram, okay, and talked about what balances what, but it's similar, okay? All right, let's move on to page 9. I want to do at least the top problem there. And so no numbers on this one. It should go a little quicker. We've got a ball. It's 0.5 kilograms suspended from a ceiling by 2 strings. the ball is at rest. Yippee, yippee, right? If it's at rest, F net for everybody is going to equal 0, right? 0 acceleration, F net equals 0. This is our Newton's first law condition. And so all the forces are going to be balanced. All the horizontal forces are balanced. All the vertical forces are balanced. Question A, is the tension in string 1, which if you look in the picture, that's the left string, is it greater than, less than, or same as the tension in string 2, which is on the right? So angles are given. Is this a mirror image? Is it symmetrical? Are they equal? No. We saw a symmetrical version on the force diagram, right? Hopefully I pointed out that because it looks mirror image, equal angles, it's attached to the middle of the object, they would be equal. But this one is not going to be same. So string 1 has a 30-degree, now watch it, it's not 30 degrees with the ceiling, it's 30 degrees from this vertical axis. So here's, where I've been warning you, draw your pictures out, don't just assume it's the same place as the previous angles. And then string 2 is 60 degrees, a greater angle, right? And so what do you think? Which string is going to be greater? If they were both at the same angle, it would be equal, right? Well, actually, maybe you don't see it. Let's actually draw a diagram here. Now, we don't know magnitude, so we can't draw it for accuracy. We can edit after we talk. But initially, your diagram, we got gravitational force down, and then string 2 is a longer string. Question, does the length of the string determine the tension? No, I'm not hinting at anything. I'm just literally telling you, don't get confused. The length of the string, note to self, length of string does not determine tension. Length is a scalar quantity, meters. Tension is a force quantity, newtons. Okay, it's a vector. Those are two independent things. But students a lot of times think, oh, the longer string has more tension. Not always true. But we do know that there's a tension force, and we've got 60 degrees. And then this one, FT2, oh, I should mix it. No, hold on. FT1, FT2, and this one is 30 degrees. And so you can use the given angles, which I'm going to do, to get your triangles. And so I'm going to switch colors for the components. FT1 is pulling it to the left and up. Now, I'm not drawn to scale, but FT2 is pulling to the right and up. And I definitely said not to scale, because what should be true about those two horizontals? Should be the same, right? And so FTX1 should equal FTX2. We should balance. There's one left, one right. They should equal. Now my picture doesn't show that, right? But they should. We can edit. We'll edit by the end to make sure they're equal. And so what does that mean about the two verticals? Well, I've got three verticals. I've got two pointed up. They're the same direction. And so our balance statement could be FT1y plus FT2y equals the one down, FG. Right? And so we need to know, together they support the weight, but it's not going to be a 50-50 breakdown, right? We want to know who's bigger in terms of hypotenuse. Well, they both have the same horizontal, so whoever has the bigger vertical component is going to be a bigger hypotenuse, yes? And so actually, we might be able to draw this out a little better. Make the x's more equal. And tell if we try to get closer to scale. And so the vertical component, we want the angle to be bigger. So this 60 degrees. And so there's the y component. And so trying to make sure that the two horizontals are equal in magnitude and try to relatively keep 60 degrees twice as big as 30. So with those closer to scale, look at our picture. Who's a bigger vertical component? Who's a bigger vertical component? String 1. Again, they both have the same x. String 1 has a bigger vertical component. And so it's going to have a greater hypotenuse if you were to do Pythagorean theorem with those. And so kind of drawing it a little closer to scale, we can see ft1y is bigger than ft2y. Okay, which means ft1 would be greater than ft2. Good deal? Now, there's another way you could think about it. 30 degrees is with the vertical, okay? So it's gonna be closer to the vertical, where 60 degrees is further from the vertical. So you can think about it having a smaller vertical component with doing the trig, okay? So, cosine 30 and then cosine 60. Okay, so we know string 1 is greater than. Now the next question, suppose that the ceiling is the ceiling of an elevator. And so now we go back to that elevator that we did last time. And the elevator is moving down. So that's an important note, the direction, it's moving down. And it says at a constant speed of 2 meters per second. So they gave us a number. Is the tension in string 1 greater than, less than, or equal, same as the tension in string 1 from above when we were at rest? What do you think? Now that we're moving down in an elevator at a constant speed of 2, how does that tension in string 1 compare to the at rest scenario? What does at rest and constant speed have in common? 0 acceleration. Tell me more about the forces. Net force equals to 0. And so we got balanced forces going on, right? Newton's first law. Isn't that what we said was true up above? To solve, didn't we balance all the forces? Constant speed, it's as if we're not moving at all, right? And so it would be the final answer would be the same. They're both equilibrium scenarios. Good deal? Now, what if it was accelerating downward? Kind of think back, what would part C be? Okay, if they were accelerating downwards, then what? Then it would be just like before, right? Or yesterday, last class, you would have an F net. Okay, we'd have to define the direction, but we would have the tension forces and then minus the gravitation. So basically right here, I said up is positive. And then you'd go m times a negative a, right? It wouldn't equal 0. They wouldn't balance just the weight. It'd be weight, we'd add. And so it would be minus out the net force, whatever it is. You'd have to know the acceleration. So it is different when you accelerate up or down, okay? The tensions are the ones that change, not your weight. Okay. Bottom one there, y'all can try. What's fun about these, and yes, AP exam does have students proposing 2 different or 3, 4 different explanations for something. So who's right, who's wrong? And so you've got 2 strings there. Notice it's a little bit different, but they're both supporting some kind of mass, okay? And I'm gonna guess they're arguing about tensions. So it's kind of similar to what we just did. Hopefully it's easier. 1 string's all in the horizontal, right? So I'll let y'all try that bottom one later. Page 10, this one, I don't think we've seen the side-by-side objects. Here we have objects connected with different strings. Shown is a spaceship pulling 4 cargo pods at a constant velocity. The pods are connected to each other by rods. And a rod connects pod A to the spaceship. So I said string, but it's going to be rods here. They don't give. Strings have a little bit of give, a little bit of stretch, right? But typically your rods don't. The velocity of the spaceship and of the pods is 5,000 meters per second. All masses are given in the diagram in terms of m. The mass of an empty pod, and you can see in the picture, pod D on the left is just m. And we're in space, so you can ignore any kind of air resistance, right? Question, rank the magnitude of the tensions at the labeled points in the rods. And so we got 4 points, A, B, C, D. Who has the greater tension? And so actually, we should start with what? What's a good place to start if it's a force problem? Step 1, draw diagram. And so the ship is going to be pulling on the rod at A, right? And so you've got this pull, or I could call FA by the ship. And then in the rod, so these are rods, it's also getting a pull back, right? And wouldn't every single BCD have the same 1 right, 1 left? Yes? Everybody has a right pull and a left pull. It's just the label, who it's by, would be different. C pulls D to the right, D pulls back to the left. And so after you draw a diagram, it would be an F net statement, right? And so maybe there's a rightward force minus a leftward force. Notice I'm being generic for a second. Everybody has 2 forces pulling on those points. And F net equals MA. Now they don't tell us those actual forces, and they don't need to. And by the way, they give us the speed, they give us mass. We don't have enough information to calculate a force based on speed alone, okay? We haven't seen that equation yet. But they did say a code word. What was the code word or phrase? Constant velocity. What's true if you have constant velocity? Acceleration is 0. So what does that mean about the right force and the left force? They're going to be the same thing. And so the way I drew them, I actually tried to keep it, equal and opposite. Newtons. Which one? Equal and opposite forces, newtons. You're thinking of the Drake meme, right? Which one is it? These are equal and opposite forces because of Newton's first law, actually. Okay? First law, whenever you balance forces on any one point, okay, and we've got multiple objects, which is maybe why there was a pause. You had more than 2 objects, more than 3. But it's Newton's first law when acceleration equals 0. If they're equal and opposite for that reason, first law. And so calculate the magnitude of the tensions. Well, if this left force is D pulling on C, and this is C pulling on D, those are equal and opposite, right? And then C and B pull on each other. And so C pulls on B, B pulls on C. And then you've got, oh, wait. Oh, yeah, and then BA and AB. And then here, the rocket pulls on A, and A pulls back on the rocket. So however you want to label that, AR, and this pull force could be labeled RA. Yes? And so we know at each point they're equal and opposite. At the end of the day, though, this is a system, yes? And so as a system, rod A is pulling which pods? A is pulling 4 pods, right? How many pods is B pulling? 3. How many pods is rod C pulling? 2. And then D is just pulling 1 pod, okay? And so you have to look at it as a system, a big system, a small system. Which rod is going to be pulling the most? Who's going to have the greatest tension? Use your gut here. The ship's pulling all of them, right? Rod D is really just pulling, supporting pod D. If something happened, if we cut the rod on D, then only pod D would leave the system. So who's going to have the greatest tension when they're all going at constant velocity? The net force is 0 on everybody, right? But when we look at it as a system within a system, A should be the greatest, then B, then C, then D. Yes? Are y'all sleepy or lost? It's kind of hard to tell. You got to ask me questions if you're lost. If you're sleepy, stand up. Walk around the back of the room. I don't mind. All right. Page 11 has some more systems. Notice you got some vertical ones. I'm going to let y'all try those. Okay, again, keys on canvas. So I'm going to put try here. And so they're not side by side, it's vertical. So maybe you label the forces a little different. Okay. And 12, I'm going to put try on this one. It's going to be very similar to one that we do on page 13. And so the last page we're going to do today is actually page 13. And it's got 2, like I said, these are free response types. And so I'm going to do my work on the side. I know it would have been better had they been spaced. I'm sorry. Number 2 at the top says a 60-kilogram woman hangs from a rope attached to the bottom of a helicopter. And so I'm not an artist, but you know, maybe here's the helicopter. I don't know. And then some kind of rope. And then we've got a woman, a person, a object. Okay. We know she's 60 kilograms. Now we don't know the mass of the helicopter, and that's okay. That's not going to be our object. Starting from rest, the helicopter accelerates upwards at a distance of 36 meters in 6 seconds. Hint, hint, sounds like what? Kinematics. So we'll probably have to do a little kinematics. The helicopter then uniformly slows to a stop in 4 seconds. And so we've got this straight up, phase one is straight up, it speeds up and then it slows down. And then before flying off to the right with an acceleration of 3 meters per second squared. After accelerating for 5 seconds to the right, the helicopter travels at a constant speed to the right. We have 3 questions telling us to solve for tension. Is there a tension equation on the formula chart? No, we have to write these equations. And so what is the tension in the rope as the helicopter accelerates upwards, 0 to 6 seconds, and then when it slows to a stop, still going straight upwards, 6 to 10 seconds. And then what's the tension as they accelerate to the right? 10 to 15 seconds. So we've got 3 phases here. And so we've got 3 kind of diagrams to draw. And so for part A, we're accelerating upwards. What would step 1 diagram for the person? What forces are acting on the person as they accelerate upwards? Got to be quick with gravity. Gravity is the every time force. What other force is acting on the person? Tension is going to be pulling what direction? Straight up. Now, I haven't drawn it yet. How big do I draw it? If you're accelerating upwards, y'all want to make up positive? We got to decide at some point. And so accelerating upwards will make the positive direction. In order to have acceleration, remember Newton's second law, acceleration happens because of a net force. Our net force has to be in that same positive direction. So how big do we draw the tension as the person accelerates upwards? Bigger than the gravitational force. Okay, Ft is bigger than Fg. Now she's just going straight up. She may not be sitting on anything, but y'all, this is just like the elevator. Except instead of normal force changing, we're going to have a changing in tension force. Tension varies, okay? But it's just like it. Any other forces? Neglect air resistance. That's it. Step 2, we're going to solve for tension. There's no equation on the formula chart, so how are we going to solve for tension? Write a summation statement. And so the net force, and this is all vertical. You don't have to include the vertical since there's only one direction, but coming up, she'll go to the right. So I'm going to go on and specify a y. We said up is positive, so positive tension minus negative gravitational force. All right. We're trying to solve for tension, so I'm going to add gravity to the other side, and I'll get tension equals F net y plus Fg. And then we plug in our variables. F net equals ma, and it's a vertical acceleration, plus Fg. Fg equals mg. Now you can factor out mass if you'd like, but you don't have to. And so we do know the mass. They said it was 60, I believe. Then acceleration. Did they give me the acceleration in that 0 to 6 seconds? No, but we can go find it. So pause on A. Let's use kinematics to solve for acceleration. And so we can assume that the person, or maybe they told us, oh, they did. Starting from rest, The helicopter goes a distance and a time. And so we know 3 kinematic terms. And if you want to call it delta X or delta Y, either way. And so 36 meters. The time is 6 seconds. No, don't go too quick. Students right here, they'll be like, oh, it's 6 meters per second squared. Don't do that. Use one of our equations, right? This is not constant velocity, it's a constant acceleration. And so we'll use our second equation. Yay, VIT zeroes out. And so then we got 36 meters equals 1/2 acceleration times t. Don't forget to square it. 6 squared is 36. And then I have to divide both sides by that time 36 squared, right? Or time squared. And so a would equal, 1/2 a, right? We could have done half of 36 first, but we get a would equal 2. And it comes out positive because we were going up 36, okay? Accelerating upwards, which we said was positive direction. And so we can plug in that 2 meters per second and then keep our fourth statement going. Same mass, 60. I'm going to use gravity 10. And so 600 plus 120. What's our tension force in the first segment? 720. Notice it's bigger than the weight, which is 600. So if she was, somehow attached to a force sensor or some kind of scale, it would appear that she weighs more, right? A little bit of elevator callback. Good on part A? Look familiar? Yeah. Part B. What is the tension as it slows to a stop? 6 to 10 seconds. And so part B, we're accelerating what direction if she's going upwards but slowing down? That's a negative acceleration, right? Meaning I need a negative net force. What would the diagram look like now? Did her weight change? Did FG change? No, so same-ish, FG down. But if you want a net force in the negative direction, now I got to draw tension. How big? Less. And so it's not only less than it was before, and maybe I call this one FT2. I changed colors, maybe you didn't. It is a different tension than up above, if that was FT1. Okay, and so it's not only smaller than the tension before, but it's smaller than the weight. That way, whenever you do your net force statement, I'm still going to say FT2 minus FG. Okay. Still going to do that because the upward direction is what we said was positive. But now we should have a negative acceleration. Should we assume it's -2? Did they tell us the distance that they came to stop? No, the only thing we know is it went from 6 to 10 seconds. So note to self, we need to actually solve for this new acceleration. And so, a little bit more kinematics. We need A2, if you will, right? Second interval, second segment. So we know the time is 6 to 10 seconds, so that's a total of 4 seconds. And we're coming to a stop, so the final velocity is 0, right? They said we come to a stop. Well, that's all that we know. They didn't tell us the distance it took. They didn't even tell us the initial velocity. But what have we learned from in the past? The initial velocity of segment 2 is equal to the final velocity of, initial of part 1. So the initial of 2 is the final of part 1. Now, do we know that? No, but we can quickly go get it. So 2 kinematics things, right? And so side note, go back up to part 1. So I'll switch back to blue. Let's find the final velocity of 1. So we know distance, we know time, go back to interval 1. We know distance, we know time, we know acceleration, we know initial velocity. We know a lot. And so pick your favorite. How are we going to solve for final velocity? First or third? First. Everybody says, why square if you don't have to? I agree with you. And so I'm just adding in the ones here because we're going back to interval 1. And so it's already solved for final. Initial started at 0. Acceleration of first interval was +2, and it happened for 6 seconds. And so the final velocity of 1 is going to be 12 meters per second. And it's positive. They were only going in the upward direction. And so now we know the initial velocity of part 2 is going to be a +12. Now, is this enough to find the acceleration of interval 2? Yeah, using what equation? Notice we don't know the distance of interval 2. So once again, we're going to use that first equation, but solve for something different. I thought we were done with kinematics, Miss Earhart. No, we're not. Okay, and when we finish forces, we won't be done with forces. We'll use forces all year long for sure. And so now we want to plug in what we know to solve for acceleration number 2. And so subtract 12 divided by 4. What's our acceleration for part 2? -3 meters per second squared. Okay, so now we know the acceleration, and it aligns with, we had said it was going to be negative, and we did. And so we get a -3. So now let's pick up with our forces, our F net statement. We're trying to solve for tension, add gravity to the other side. And so FT2 equals F net Y plus FG. And so F net equals Newton's second law, MA plus MG, same as before. Mass is still 60, but now acceleration is -3, and then 60 times 10. And notice, we're going to get an answer less than the weight, right? We get -180. We get less than the weight. We get what? 420. So FT2 is less than your weight. Does that make sense? Maybe you've never been dangled from a helicopter, but go back in that elevator. This is very similar. It's not just on the fall down that you feel like you might come off your seat, but as they approach the top of the building, or if you go back to Superman, right? As you come towards the top, they can't continue speeding you up, right? They got to slow you down. You don't want to launch off the ride, okay, or out of the elevator. And so that slowing down on the way up is a negative acceleration. You feel lighter. Your scale would actually weigh less, okay? Tension is smaller. Yes. Everybody good there? Okay. And so now for part C, now we're going to start moving to the right. And remember, up there, they did come to a stop. So we're starting back at rest. And here's kind of some new piece. What we've done so far, kind of old. You're seeing it again. But here comes a little bit of new. So now we're going to accelerate to the right. So I've got my microphone here. It's a mass. It's hanging from a string. Now I know there's two strings, but they'll work together. So imagine it's one string. So imagine I've lifted it up and then I've slowed it to a stop. And now I want to accelerate myself to the right. The microphone is just going to come along for the ride. Now physics happens fast. You've got to watch the microphone, watch the string as I accelerate to the right. I'm not going to push the microphone. I'm just going to keep hold of the string. In 3, 2, 1. Did you see, not the slow down. Did you see that speed up? Watch the microphone. In 3, 2, 1. Now, if you saw it, I'm starting in line with the microphone, but when I move forward, does the microphone immediately come with me? Objects at rest, microphone. Want to stay at rest, and I'll do it again. In 3, 2, 1. Oh, hold on. I faked that one. I kept my arm still. Okay. 3, 2, 3, 2, 1. Okay, so I kept my arm as a rod. Okay, but did you notice that when I accelerated, the microphone, the string was a diagonal? Yes? Now, whenever I came to a stop, watch me come to a stop. I don't know if they have us go there, but now I'm going to accelerate, but watch my stop. Watch the microphone, okay? 3, 2, 1. What did the microphone do when I came to a stop? It was in motion, so it kept going forward until the string tilted the other way. So if you think too quick, you think, oh, when the person goes forward, the microphone goes forward, but actually the microphone appears to go back. Does it really go back? No, it just stays put until the string pulls it, right? What if I walk at a constant velocity? String is straight up and down, right? It's like it's at rest. Okay, so hopefully that helped, okay? This is the same thing that happens, you know, page 12 is going to talk about something hanging off a car bumper, okay? Cans off of a bumper. Same thing if you have something dangling, an air freshener, fuzzy dye, something in your car. When you go forward, the fuzzy dice wants to stay back. It doesn't move backwards, but in that acceleration moment, it wants to stay back, okay? Okay, so what is the tension in the rope as the helicopter accelerates to the right? And so our picture is going to look a little different. And so C is accelerating to the right. And so if the helicopter moves to the right, our lady dangling appears to be on what side? Just for the moment, while it accelerates, is the lady going to be on the right? Is it like this? Is the lady on the, oh wait, hold on. Here's our lady. And so if the helicopter goes to the right, she's going to appear to stay on the left, right? Correct? Okay. And so the string is actually going to pull her to the right. And then gravity, of course, down. Now it kind of looks like those are equal forces. Let's correct that, okay? Hopefully we've done enough of these. Which one should be bigger? Because I kind of have them drawn equally. They shouldn't be. Which force should be bigger? Well, let's figure it out. Let's draw some components. We'll draw it and then we'll edit as we go. Notice your tension force is at an angle. And so we've got two components, X component of the tension and Y component of the tension. Now she's accelerating to the right. So hopefully it makes sense that F net is to the right if your acceleration is to the right. But vertically, is she moving vertically anymore? No, they stopped that vertical motion. And so what is the net force in the vertical? 0. So I'm going to add x's up there, but vertically, AY is going to be 0. There's no motion whatsoever in the vertical anymore. And so F net in the vertical should equal 0. What does that mean about my two vertical forces? They should be the same. And so maybe we just add tick marks here. Okay. And so with that, which force is bigger? Think about your right triangles, a little bit of not mental trig, don't do sine cosine in your head, but look at components and hypotenuse. FT should be bigger, okay? And so FT is bigger than FG. And that's because your vertical forces balance out, okay? FTY is going to balance your FG. Good there? Okay. And so now we got to solve for, they actually want the tension, which is the hypotenuse. Well, I can't solve for the hypotenuse with F net, but can't I solve for the components? So if we solve for FTX and FTY, the last thing we'll do is Pythagorean theorem to find the hypotenuse, okay? And so just note to self, the tension that we're looking for is the hypotenuse. And so the quickest one to solve for is the vertical because it's equal to the weight. And so let's keep that sentence going. FG equals mg. And they told us the mass of the lady is 60, gravity's 10. And so we know 600 newtons is the vertical component. Now let me go, did they tell us the angle that it makes? We could be solving for it later. Yeah, we're going to solve for it next. So I can't just go straight for SOHCAHTOA. I got to be able to do this without the angle, okay? And so, like we said, Pythagorean theorem at the end. And so now let's focus on that F net x. And so the only horizontal force is that tension in the horizontal. Well, I don't know the tension in the horizontal. That's what I'm trying to solve for. But what does F net equal? Newton's second law, F net equals ma. So we know mass is 60. Do we know the acceleration now in the horizontal? No, but maybe they gave us enough to solve for it, right? I definitely remember they gave us the time. It was 10 to 15 seconds. Oh, no, never mind. They did give it to us. Flying off to the right, 3 meters per second squared. Aren't they so nice? We don't have to do kinematics again, okay? And so they gave us the acceleration, and to the right, there's no mention of left. We can call to the right positive. And so we know that the x component of tension is equal to 180. And so now if we focus, I'm going to zoom in or draw a little bit bigger, that tension force that we're looking for. Without knowing the angle, we know that the vertical component is 180. Oh, no, I got it backwards. Horizontal is 180, so not drawn to scale. The vertical is 600. How do we find the tension in the actual rope? Pythagorean theorem. So grab your calculator. 180 squared plus 600 squared is going to equal the tension, the hypotenuse that I'm looking for. So I'm going to call this FT3. It's our third interval, right? Let me know what you get. Remember earlier, we predicted it should be greater than 600. Hopefully you see with our Pythagorean setup, it should come out greater than 600. When you get an answer, let me know. 626 point what? 4. Okay. So I'm just going to keep it 626 there. Somewhat appreciation for sig figs, right? So 626 newtons is bigger than the weight 600 newtons. Everybody good? And I'm going to stay on this screen. They also said, part D, what's the angle that the rope makes with, oh, I do need to go see. Do we want the angle with the horizontal or angle with the vertical? What angle did the rope make with the vertical? And so now in my triangle, I'm going to label the angle that touches the vertical. Okay. Now I know all sides of the triangle. Y'all, this is just vector stuff again. And so how am I going to solve for the angle? What's one way? Pick your favorite. Inverse tan we can do. So theta would equal inverse tan. And based on my picture, again, students don't always draw the picture. I've labeled the angle based on that. Opposite would be 180. And then adjacent to theta would be the 600. And so going in inverse tan, whatever you get. Let me know what you get. Got an answer yet?
16.6.
16.6, or you could call it 17, either way. And so it's with the vertical. I mean, that's what they're asking for. That's what they would grade for. If you stated the horizontal angle, you better say with the horizontal, but then I would say, you know, answer their question. They said, what's the angle with the vertical? Give it to them. Good deal? Okay, and then one more here. E says, what is the tension in the rope after the helicopter stops accelerating and begins moving at a constant speed towards the right? I kind of set us up for that. Luckily, I didn't read ahead, but when I was walking with the microphone at a constant speed, what angle did it make? Let me do it again. Walking with the microphone. Now I'm going to have to accelerate a little bit, but then I'm going to walk at a constant speed. Watch what angle the microphone rope makes with the vertical. So constant speed. What do we see? Straight up and down. And so it makes a 0-degree angle with the vertical. Gee, what would our diagram look like on part E? Gravity down. Tension would be straight up, and you're walking a constant speed, so these two forces should be equal and opposite Newton's first law. Notice I didn't slide back over. I don't need a lot of room. Tension now is going to equal Fg, which we've already solved it several times, but it's mass times gravity. 60 times 10 would be 600 newtons. Equilibrium again, right? Questions on the person hanging from a helicopter. And I know that you're like, man, that was a lot. But if you take a step back and look at all that, we got kinematics in there. There was speeding up, slowing down. We got to do some net force statements in one dimension. And then when the helicopter moved to the right, we did net force statements in 2 dimensions. Okay. And they could ask an F. What about when the helicopter slows down? Then your diagram would have an angle, but it would be reversed. Objects in motion want to stay in motion, right? So tension would be pulling back on the lady, okay? So it's a very blended type of problem. AP loves those. They love the blended. Okay, let me just see if I can get number 3 started. We're not going to have time to finish it, so I'll put, finish it later. This one, you can maybe tell by the picture, no angles, okay? No angles. 2 boxes are sitting next to each other. So this is kind of like what we saw last time, the stack of books side by side on a flat, smooth surface. We love smooth surfaces. What are they telling us there? No friction. So force of friction, 0. And it's flat, no angles, no ramp. The box on the left is 4 kilograms, and the box on the right, now not because it's bigger looking. Y'all remember density, right? Small objects can be heavier than big objects. Styrofoam versus some kind of metal. Okay. Emily begins pushing to the left on the 6 kilogram box. So not that I'm drawing a force diagram, I'm just adding whatever they're telling me here. Emily pushes to the left on the 6 kilogram box. And as a result, the box accelerates from rest to 6 meters per second, final velocity, in 3 seconds. Sounds like what to me? Kinematics. And then 3 questions. How much force did Emily apply? In other words, FA equals what? And maybe even before that, I would say part A should be draw the free body diagrams for each of the boxes. And remember, like we did with the stack of books, you can also draw a force diagram for the system. Isn't Emily really accelerating the system? So honestly, there's 3 force diagrams. Let's try and draw that. 4 kilogram. What forces are acting on the 4 kilogram? Gravity down. Then what? There is a surface. Normal, up. And there's no vertical motion here, so those 2 are equal and opposite. Now Emily's not touching the 4. Who's touching the 4? The 6 block is pushing the 4 block what direction? To the left. Watch how I label this. The force on 4 by 6. And there's no friction, nothing else. That's it. What about the 6 kilogram block? What forces are acting on the 6 kilogram block? A bigger gravity. So maybe I make these a little different, right? FG4. FG6, or you can call it AB. Still not moving vertically. Then we have a bigger normal force. These 2 forces are equal and opposite. Then what? What's another force on the 6? Emily's pushing on the 6 block. What direction? To the left. So this is an applied force. And again, that's the one we're looking for. There's one more force on the 6. This one is the one that students are going to miss. 6 pushes on 4. Newton's third law says, doesn't the 4 push back on the 6? What direction is this force by 4 on? To the right. Watch this. Force on 6 by 4. And watchy watch. Tick marks 1, 2, 3, 1, 2, 3. What are these forces? They're reversible. They're equal and opposite on 2 different objects. What does Drake say about that? These are your Newton's third law, action-reaction pair. You had to have 2 diagrams though. Last one, go with me real quick. What about the system? The 10 kilogram system. What forces are acting on the system? An even bigger gravitational force on my 10 kilogram system. An even bigger normal force on the 10. So maybe I put stars. And then you just have the applied force. So as a system, it might be easier. United States of America, to the Republic